Hi, this is Mr. Anderson, and today I'm going to talk about radioactive decay, or radiation for
Lori,
What is radiation? Radiation is essentially parts of atoms that are given off,
you know,
or
getting
energy
here.
that's given off by radioactive
Lori.
atoms. And so we measure that using a Geiger counter. This is a Geiger counter right here. And Geiger counter inside this wand, you have some inert gases that every time they get hit by a piece of radiation, they give off a little bit of an electrical charge, which you can pick up in here. And so a regular Geiger counter, when you turn it on, you're going to hear a little bit of static. And the reason why is that there's always background radiation everywhere. But if we put something radioactive in front of it, so let's say we put a big chunk of uranium-238, it's going to give off a huge amount of radiation.
Oh my God! Look at here! This is a prank! So long.
We can use that to do a lot of important things, like, for example, date how old the Earth is.
I don't have to go here.
So, how does radiation work? Well, to understand radiation, you have to understand the fundamental forces that we have. And so, if this up here is a nucleus, so the red ones are going to be the protons and blue ones are going to be the neutrons. What we find is if we look low on the periodic table, so this is neon, neon's going to have 10 protons and 10 neutrons. But as we move up the periodic table, so here we got the same number of protons and the same number of neutrons for calcium. When we move up to tin, you'll find that the number of protons is going to decrease compared to the number of neutrons that we have. And if we get up to uranium, we have 92 protons but 146 neutrons. Well, why is that? Well, the reason why is that the nucleus is held together using something called the strong nuclear force. And so all these nucleons are held together by this force which holds the nucleus together. Now the nucleus would love to shoot apart, and the reason it would love to shoot apart is you have all these positive charges up here, all these positive protons, and when you have a small enough atom, the strong nuclear force is able to hold it together. But when you get something like uranium, it's got 92 protons in the center, and so you have to have tons of neutrons to hold it together. And even with those tons of neutrons that you have, sometimes it has a tendency to fall apart. And so this chart takes a second to get your head around it, but essentially what we have on the bottom is the number of protons, and then on the side we have the number of neutrons. And so you would think if the number of protons and neutrons are always equal, then we have this perfect line that goes up here. But as I showed you on the last slide, we tend to get more neutrons the farther we go up. And so you can see that this graph tends to drift towards the neutrons. So as you get way up here with like 82 protons, the perfect number of neutrons to have would be 126. And so what you find is that if an atom exists on either side of this perfect line right here, it's going to give off protons, neutrons, so sometimes they're going to change just to get back to that equal point, or that perfect ratio of neutrons to protons. And so this chart is neat in that it shows you what kind of decay we have. So if you're on this side of this line, you're going to undergo what's called beta minus decay. If you're on this side, you're going to undergo what's called beta plus decay. And then as we get up towards here at the end, you're going to have a lot of what's called alpha decay. And then eventually we can have fission as we go far enough up. And so all of these types of radiation are ways for an atom to get back to that perfect ratio of neutrons to protons. Okay, so I've talked about
activity was actually here.
radiation.
Yes, I know.
What
Isn't
is
it right
this
here?
radiation?
I know.
Radiation works like this.
Really?
You can imagine the
You
first
must be alone
experiment.
here.
If we take a radioactive material and then we allow it to shoot its way through
I'm glad you
this,
were
and then we have a sensor over
for
here.
real.
If you have something radioactive here and then a tunnel right here, what you'll get is a spot showing up, or radiation showing up on this side. So what scientists want to do is they want to figure out what's the nature of this radiation. So what they did is they put a positive charge up here
I don't know your
and then a
place.
negative charge down here.
Miracle dash.
If I remember right, they actually have negative.
You're having a
It doesn't matter. So what they found is that you had one spot showing up down here. So there was some particle that was going out that didn't have a charge. We had some that was actually being drawn in this direction. And then we had some that was being drawn in the other direction. And so we called these things alpha decay. Alpha decay has a positive charge, and so it would be drawn towards the negative. So we're going to have alpha decay down here. Like that. We're going to have beta decay up here. Beta decay had a negative charge, so it's drawn towards the positive. And then we have this gamma radiation here that we have.
I know.
So what are these types of radiation? First of all, if we look at alpha decay is simply
I don't care.
2 protons
Make one
and 2
trick.
neutrons that are given off. And so without electrons, what is this? It's essentially helium. Helium has 2 protons, it has a mass number of 4, and so that's alpha decay. Alpha decay can't even move through a piece of paper, and so it's weak as far as that goes. Next type is called beta decay. Beta decay is an electron, essentially. An electron has a -1 charge and it has no mass. And so that's beta decay. There's another type of beta decay, and it's weird to write an electron, but it has a positive charge and it also has 0 mass. And so we refer to that as a positive electron, or we call that a positive. But beta decay would be stopped by invisible aluminum foil. And then the last type of decay, the one that doesn't have a positive or a negative charge, is called gamma radiation. Gamma radiation occurs when we have, remember, these strong nuclear forces that are holding this nucleus together. And as they start to wiggle and these atoms or the nucleons wiggle underneath their force, that energy is given off in the form of gamma radiation. It's not actually made of nucleons, neutrons or protons, but it has a huge amount of energy. It's like X-rays. It can only be stopped
I did.
large.
Oh no, I wasn't.
So
Inside.
and so those are the types of radiation.
Knowledge.
These are
Well,
the types
with
of
my
radiation
knowledge,
you should understand.
I don't
And so
know.
you also have to write nuclear formulas. And so when we did
There's something
chemical reactions and
Really?
chemical
Sorry.
formulas, remember we had to balance those equations, and you have to do the
Happens
same
all
thing here.
Well,
And so let's start with the one that I talked about at the beginning. So let's start with uranium-238. Now uranium-238 is undergoing,
Trouble. How
in
long?
other words, it's
I
going
know,
to lose,
right.
let's go back for just a second, it's going to lose 2 protons and 2
Hang
neutrons.
on, kid.
And so what it's losing is actually a helium nucleus, and so that has a charge of 2 protons. It has a mass number of 4, since there are 2 protons and 2 neutrons. And so if you think about it, what does this become?
Right.
Well, I'm actually going to
goodness,
start
looking
with
down
my
the
atomic
hole.
number and my mass number.
Miracle dash
If you
you fit.
lose 2
Sorry.
protons, you're going to have a mass, or an atomic mass now, of 90. And if you lose a mass of 4, this is going to become 234. Now what's interesting in the nuclear reaction is we've actually changed the number of protons. Since you lost 2 protons, it's not uranium anymore. And so if I look up here, here's uranium on my periodic table. But if I lose 2 protons from that, it's not uranium anymore, it's going to be thorium. And so this is how you write a nuclear equation. You have to make sure that these all balance. The mass numbers balance and the atomic numbers balance as well. So what happens to uranium-238? It actually becomes thorium-234 over time as it loses these protons. Okay, let's try another one of those. And so let's say this time we're dealing with beta decay. So let's say we lose an electron. Electron, remember, has a -1 charge. It doesn't have a mass. And so what's something that undergoes beta minus decay?
Disaster and death.
Would be cesium-137. So cesium-137 has a mass number of 137 and an atomic number of 55. And so what happens when it undergoes beta minus decay? Well, let's not write the symbol, remember, because that symbol may change. If we've got 55 protons and we lose 1 electron, what we actually gain is a proton. So this becomes 56. Where did it come from? One of those neutrons became a proton and gave off this electron. So this becomes 56. What is the mass number? Well, electrons don't have a mass. So that's going to be a mass of where it's a negligible.
Really?
And so what does this become? Well, we'd have to find cesium on here. Cesium is 55.
You're Peter.
Okay, so here's cesium right here. Cesium is 55 on the periodic table, but since we're gaining 1 proton, that actually becomes barium. And so this is going to become barium-137 plus that electron, which has a -1.
Hey, sweetie.
And so this would be, we call this beta minus decay. Okay, let's do another type of decay. And this decay we'll do is beta plus decay. So what do you lose in beta plus decay? You're losing an electron, but this is a positron, so it actually has a positive 1 charge. It has a mass of 1. What's something that undergoes beta plus decay would be sodium. Sodium has an
Case
atomic number of
closed.
11 and a mass number of
You must be
22.
alone.
And so if we lose a positron, so if we lose one of these with the mass of this, what do we get?
I wasn't
Well, we're
alone.
going from 11 mass number, or atomic number of 11. We're
Well, then
losing
you
one
were
of these, so
having
this now
hope.
becomes 10.
You must have been here.
This is
No,
not
you
changed at all,
wasn't.
so that remains at 22.
Okay, you're
And so
gonna
let's look on our periodic table.
You're great
Well,
up
here's
here.
sodium right here. It's
I
number
wasn't me
11.
alone.
But if we lose
Don't
one
be alone
proton,
here,
we now
everyone.
become
No.
helium. And so
Don't be
when
nervous.
you're doing these
We don't have
equations
to
and writing
alone.
out the formulas, make sure that you
That's
go
a
all the way across the
Time
top.
to
So we've
break
lost one
everyone
of these,
in radioactive.
all the way across the top here, and make
Radioactive.
sure
If
that
I
we
had- You come
balance
to
those
the
out.
heaven
In other
room,
words,
and
the
Jimmy
atomic
has me
numbers
alone.
and
We
the
don't
mass
have
numbers
noodles.
of the reactants and the products.
Your bitch has me for
So that's
annoying
radioactive decay, and I
active.
hope that's helpful.